Hello, and welcome back to Learning with Lee. In today's episode, we are going to take a look at allocators and how they can be used in order to insulate your particular data structures from some of the nuances of memory management. Typically, allocators are taught at the same time as iterators or shortly thereafter, which is why I'm releasing this episode now. I'm a bit trepidatious about doing so because some of the topics in here are even more advanced than what we've already covered with things such as pointers, dynamic memory allocation, as well as also iterators. And that's because we're going to introduce the concept of pages in memory. And it's not an overly complicated idea. However, traditionally this is taught a bit later on once we get into how operating systems work and some of their low-level structures. So, we're going to cover this now, and we're going to give a brief overview of what pages are. However, you can expect a more full overview of paging and what the value of it is at a later point in this series. For now, the reason why we're covering allocators shortly after iterators is that allocators, like iterators, are an abstraction of memory management. In iterators' cases, we were going through something like our linked list, and we wanted to hide the fact that with each one of these we had to jump to a different spot in memory. Whereas with, say, an array, and we can just pretend like this is an array for now, I can just go from this spot up here to this spot here, and then jump down to here, or head back up to here as I see fit, because it's a contiguous block of memory, and that can all be hidden for us behind an iterator, so as that we don't necessarily care exactly how it's laid out in memory. Allocators do a very similar thing. An allocator's job is to hide the portions of, basically, in case you remember how we would do something such as new link. And for this, it happens to be fairly easy in order to understand why we ended up doing this when we wanted a new link here. However, behind the scenes, that would end up basically going, okay, I need to create some chunk of memory, and then I need to initialize the values in that memory accordingly, based upon link, based upon its parents, etc. And allocators are designed in order to hide some of the implementation of that, such as malloc calls and the like, from you and from your data structures. And while it doesn't make as much sense to necessarily use an allocator with our previous example of a linked list here, it does make more sense when you're dealing with a dynamically sized array. And I know that so far the only arrays we've seen have been statically sized. However, within C++, and I mentioned this a couple times, is what's known as a vector class. And the vector class is basically an array that uses an allocator so as it can be dynamically sized. So as that basically what it is it's like, okay, I'm adding in elements, and all of a sudden I run out of memory at a certain point, let's say down here, and then I need to add in additional elements, but I need more memory. So what it's going to do is it's going to need to end up going, okay, I need to create another set of memory over here that now has additional elements at the bottom of it, and basically has more space than this first one. I then need to copy this stuff over, and I need to delete this stuff here. And normally you'd have to do that on your own using malloc calls, using free, and these are all things we've gone over earlier, in order to manually and forcefully do this general process of handling the memory yourself. And allocators are designed to alleviate that for you and to handle it for you. And basically any container in the standard library uses allocators rather than directly referencing memory, with possibly a few exceptions, but for the most part, at least to my knowledge, all of them end up using allocator, or a variant thereon. In our case, there is actually a good justification for using allocators, and that's because normally right now we're just using new link and we're allowing our compiler to automatically handle the allocation for us, for finding where it is and then for then creating it at that location. And I'm splitting this up into two steps here, whereas normally you just would view it as the single new step right here. Or if you want to, you could view it as the new step followed by the constructor afterwards, and sort of treat those as the two different steps, where the new happens to be allocating the memory, and then the constructor is actually initializing the object. And allocator, the class itself, and as you can see down here, it is a templated class, so as you can supply it something such as a link, And the reason why it's templated is so as that you can end up doing something such as, this could be an array of links, it could be an array of integers, it could be an array of some other class that could be very large or very small in size. But Allocator needs to know how large that class is so that it can end up creating a certain chunk of memory, as well as in case then I want to use the allocator to then initialize that chunk of memory, I need to be able to call the new operator on whatever templated type is in there. So that should make it clear why there happen to be these 6 different functions here. Because the first thing that you have is you have your allocate function. And what that's going to say is I need to allocate some block of memory. And in this case here, size n, really what this is happens to be the number of elements you want to initialize. So basically what you're going to do is it's basically the same as doing malloc of whatever this number is times the size of whatever your template is. And that's going to give you some chunk of memory of that size, or it's going to throw an error. Then you can do this, which is what really separates allocate apart from just calling malloc or calloc or realloc. And that happens to be that you can give it this pointer hint. And there's a very good reason why you would want to do that. And let's take a look at our linked list here. Let's say that I want to insert an element in between A and double Z here. And this element over here that's brand new, and we'll just call this one N for now, and it happens to be, we need to figure out where we want to put that in memory. And basically, this brings us to paging. And memory, by your operating system, happens to be split into pages. So you might have a page, so we'll just call these P0, P1, etc. And whenever you end up using memory, it'll end up allocating a certain number of pages for your program. And not always will your entire program be loaded into memory. And we'll get into the exact details of how that works and why that works in the future, because it's not tremendously complicated, but it is an in-depth thing that deserves at least 1 and probably 2 or 3 episodes to fully cover all the details of it. And the important thing to note is that occasionally some of these pages will be in your memory. So basically, in case you know what RAM is and you've inserted those little sticks onto your motherboard before, it'll be in RAM, it'll be in your memory. However, some of it will also be sitting off on your hard drive somewhere. So let's just say that you have your hard drive over here, and this happens to be where some of the different pages that currently aren't in use happen to be. So if you have a really large data structure here, it might cover multiple pages. Frankly, for really large data structures that are handled at an industrial level, you're going to be dealing with a massive number of pages, and for certain versions and certain file systems that are designed to handle larger files, you might have larger pages than something like Windows typically provides. But it's a matter of what you have to do then is you occasionally have to load in a page off of your hard drive, and that might also necessitate unloading a different page so as that you basically can limit how much memory a certain program has. As a result, what you typically want is you want your data to all be on the same page if you're going to be using that data together very frequently. So in this case here, I would want N to be on the same page as ZZ, because typically I'm going to be going through this list, and then I'm going to want to access N after I've accessed ZZ. Occasionally I'll want to go backwards, but if I'm going backwards, I'm typically going to want to go to N and then continue back through ZZ, ZY, etc. So it makes a very large amount of sense to want this to be on the same page as ZZ. And that's what this pointer hint does. It doesn't guarantee that you'll wind up on that same page, but says, hey, start looking near. And basically what this pointer would be is I would have some pointer here, and this would be my little hint pointer to ZZ. And it would say, start looking from that spot in this page. And you think about how I had discussed earlier, how these are just divided into little address things. It's sort of like we have our little P.O. boxes within this page. And some of it's also because memory is also described in terms of words, where one word basically translates to one address in terms of how much is allocated for it. So you might have some chunk of memory up here, and then basically you could go to the next one, and so on and so forth down through this page. But the goal is that you start at one spot in memory where your hint is, and then you look for the next open spot that can fit the amount of memory you're trying to allocate. So that ends up being why you'd want to go with this hint here, so as that you can basically go, I want to group together n with zz. To give a even more clear reason why you'd want to use this hint, let's take a look at a binary search tree. And we'll be getting into binary search trees probably within the next couple of weeks or so, just because of the fact that once we're done with I/O, which is what we'll be covering after this episode, we're going to probably be moving into data structures, and one of the most important ones is a binary search tree. It is a very frequently used data structure for efficient lookup and efficient insertion of data, so as you can end up easily having sorted data at your disposal. However, one of the important things about it, and one of the concepts we'll be getting into, is that basically with this sort of a tree, once you move off of this parent node, you effectively have two different trees that happen to be its children. And you can see how this would sort of be a recursive way of going, I have this tree that has a pointer to two other trees that themselves have pointers to two other trees, and they might even have pointers back to their parents. Because while that takes up additional memory, it's a bit more efficient for some of the operations to already have that defined. However, then you can see, okay, we've got subtree here, and so on and so forth. And as a result, most of your operations within here are going to be on these localized trees. Typically, it doesn't matter whether free and C are close to each other in memory, because of the fact that there's this sort of division between one tree and the other. Same thing for down here. However, it's a matter of what really matters is that I'm typically going to be going down one path, and I'm going to follow it down to one of its children, and so on and so forth. And what's going to end up happening is that within here, I'm going to want this to be more clustered in memory together than this is, or more accurately, than free and C are, because their relation is much more loose than this parent-child relationship is. And to a certain extent, the fact that we're going to want them to be closely related to their parent does happen to mean that they're going to inevitably, most likely, wind up being close together in memory, but it's not as important as keeping these together, because you're going to be operating on this subtree altogether more often than you're going to be operating on these two together. So that happens to be why you might also provide a hint, such as in case I were to insert a brand new child somewhere. Let's say that I want to insert one off of here, and what these are known as in parlance, because these are known as trees, is these are leaves. Basically, they happen to be a tree with no children. But let's say I want to insert a new leaf down here. And for now, we're just going to ignore the fact. Well, actually, for this, we're just going to insert this one into here. And what's going to be important about this now is that with that, we're going to want to end up having it close to G. So we'll want to supply this leaf, or pointer to that leaf, as our hint. And what it's going to then do is go, okay, we're going to supply n of 1, because it already knows the size of one of these based upon this t here. We don't need to supply that as part of n. We just need to supply an argument of 1 here, and then we need to supply the pointer to G itself, so as we can end up being like, okay, we want close in memory to G. So as it makes it a bit more efficient in terms of our paging when we're ending up doing that. And we'll be getting into a lot of how to optimize this in the future, and why you would actually care about this once we start getting into algorithms, once we start getting into different aspects of how operating systems work. Then, the important thing to note, though, about allocate is that allocate doesn't actually effectively do... You remember how I said new link could effectively be described as two different things. It has its constructor, and it has the new operator. Well, allocate is effectively this new operator, and that's creating that spot in memory. However, we aren't yet calling the constructor. And that's what construct is for. And it ends up then creating our link, or creating whatever type of element we have for this t, at the location that's pointed to it, And I've left args as sort of this vague italicized thing right now, and that's because it's changing depending on whether you're using the 98 standard, i.e. 1998 standard for C++, or the 2011 standard for C++. And this is going to be compiler dependent, and it will vary significantly depending on which variety it is. And the way in which you end up supplying it is somewhat different, because in the old style, typically what you would do is it would call the copy constructor. So basically I would have to pass into here some other link in order to copy into it. However, in the new one, basically what it's going to do is it's going to take in a reference to a reference. So basically think about similar to how you would have a pointer to an array of pointers, in which each one of those pointers can be a custom type, so as that you can end up basically packing in some memory with all the different arguments that you want to supply to this link. And then what you're going to end up doing with that happens to be, it can then parse those out and supply those as the correct arguments to that type. However, that's the brand new way of doing it, and not all compilers have that implemented, so that's something that you might have to wait a little bit on before you can actually use it. Then, conversely, and you can sort of think of this in terms of the order in which you would have to call these during the lifetime of one of these links, is that initially you have to allocate the memory for it, then you have to construct it, then when you're done using it, before you can deallocate the memory, you have to destroy the object. And you can think about that as then that's going to call the object's destructor. You remember basically the same as having the link here, except as opposed to new, it has a tilde in front of it. So that ends up doing that in order to destroy the object, delete any of its dynamically allocated memory, etc. And then, number 4, you deallocate this memory itself. And part of the reason why you end up having this split between allocate and construct is for things such as your arrays and for your vectors that I was mentioning earlier. And that's because of the fact that occasionally you might want to initialize a vector with a certain amount of space. And by default, it's going to have more space than it inherently needs, because having to search for new memory every time you insert an element into a either array or even a linked list, with an array it's a bit more expensive, because in case you can't just expand your list by 1, you have to find a large chunk of memory that's equal to the size of your array plus 1. And that can be fairly expensive to do at every iteration of adding something into your list. So it makes a lot of sense to be able to allocate a large chunk of memory before you end up having to actually create any of the elements in there. Or then when I want to reallocate that vector, such as in case I'm nearing the end or have reached the end of my initial size of the vector, and I want to add on, let's say, another 100 elements, or space for another 100 elements, so as I can just keep inserting without having to do 100 additional calls to allocate, as well as then copying it all over, and then destroying the old array, which is basically what you have to do whenever you end up doing this, unless, of course, you can end up reusing the same chunk of memory, which is fairly rare to actually have that opportunity. So, it's one of the reasons why I said that using the heap is more expensive, but that is why you end up splitting these up, is so as that you don't always have to construct it when you allocate it. However, you do have to have it allocated before you can construct it. You want to destroy something before you deallocate it, because otherwise you're going to have memory leaks. And that's really the 4 major things the allocator does for you, is that it hides that searching for new memory on your heap in order to basically insulate your different data structures from having to do that. And to a certain extent, that's done for you when you use new, but in case you have a more low-level data structure than what we did with our linked list, you'll want to use allocators in order to end up easing that for you, so that you don't have to do that yourself, and you might end up writing your own custom one. Lastly, there's a couple of other things. Max size is basically, it's going to find the maximum size of an array that you can currently create using the memory that's available to you. That said, in case you call max size, basically if you call max size, it gives you a value back, and then you try to allocate that, there is a chance in multi-threaded environments that that chunk of memory will have already been used up. There's a chance that something else that might be running, or some of the operations itself within either max size or within allocate might end up shrinking that slightly, so you might not necessarily be able to successfully get something of max size. So just because this returns a certain value doesn't necessarily mean you will be able to get that value out. You probably will, but it's not guaranteed. Lastly, there's address of basically you pass in some reference. So that would be the same as in case I had some link L here and I called L with the ampersand on it and I assigned that to a pointer. But basically you just pass in your link or pass in whatever type of T you have into there. And then what it's going to do for this is it's going to give you back a pointer to that object. So it's useful in case you end up having a bit more indirection possibly within there. So in case you have a special version of Allocator for some type of object and you want to hide more specifically the actual location of something, and basically your R is either itself then a pointer to something else and you want to do some indirection that way, that's a way of abstracting that out so as that you can end up hiding that. But the major four are these four up here, and I think that's a good enough overview of allocators for now. Frankly, I myself have never had to create a custom one in my professional experience, and I haven't even really had to use the original version of Allocator with my own custom T for any stuff that I've in general done. It's useful to understand how the standard library works, but that's really about the extent of it for the most part. It takes some really rare and special jobs where you end up actually having to create your own custom allocators or use Allocator itself directly. So, thank you very much for watching. Have a wonderful day.